1.8 volt, but there is no current control. 2.3 volt, no current control. Let's control the current now. Now our power supply is in 1 ampere constant current. If we want to increase the voltage will not increase because the system is in constant current mode. At 5 volts, these two items are drawing 2.265 ampere current. But now if I will decrease the current is being controlled, the voltage will drop because this time this circuit is working in constant current mode. Assalamu alaikum wa rahmatullahi wa barakatuhu. Friends, welcome back to my channel. In last video we created this linear regulated DC power supply. I used LM324, one section, one operational amplifier with coarse adjustment and fine adjustment. We controlled the voltage. I applied 28 volts. This is common and this is 28 volt line. 28 volt are provided to this transistor that is being controlled by this operational amplifier from here. This circuit don't have current setting, current control. I used two different power supplies. The one power supply will provide high voltage 28 volt that we are controlling by this transistor. And this 12 volt power supply is used to power on this IC. In next stage, we will connect transformer for 35 volt, 30 volt, any voltage value which we want to control. Just only we need to readjust the feedback network. We need to understand this resistor value, that is feedback resistor, from this voltage divider network. If you want to control 60 volt, that time we need to readjust the value of this resistor. But for this time I will use 28 volt from this power supply. I used 10 ampere transistor. When we are using in power supply, it is best practice to use 1/3 ratio. If it is 15 ampere transistor, we will take maximum 5 ampere for its safe operation. Although we can reach up to 10 ampere because it will dissipate power all the time. This time we don't have any current control. Now we will add current control in this circuit so that we can take constant voltage or constant current. Now I will increase this heatsink size. Because this heatsink is smaller in size, it will not dissipate power at continuous operation. Because switching power supplies dissipate less power, MOSFETs, but linear transistors, BJTs, dissipate power during all operation time. .8 volt, but there is no current control. 2.3 volt, no current control. Let's control the current now. We occupied one section of this LM324. Now we will utilize the other remaining 3 sections. Current sense circuit is very critical, precise and sensitive circuit. So we need a special care while designing this circuit. We need a current sense resistor in the ground side. This is positive output and this is ground. We need a resistor here that will be connected in the low side. So its resistor value must be low because it will also dissipate power. This is our power supply output return line. In this line we will connect a resistor. Then it will output. Before this we were taking output from here, but now we will take output from this resistor. This resistor value must be low. We will use 0.1 ohm 5 watt resistor. 0.1 ohm 5 watt. Let's suppose we are considering output current 5 ampere. Resistor value 0.1 ohm. Its power rating P is equal to I square R. 5 ampere square multiply with 0.1, so it will 2.5 watt. So 5 watt resistor will excellent. We can use 3 watt, but safe range 5 watt for 5 ampere current. If we will use 1 ohm resistor, 5 ampere current multiply with 1, 25 watt. So 1 ohm resistor will very large in size and that will dissipate power too much. But here we can compromise on 2.5 watt at full rated operation. So if 5 ampere current will flow from this circuit, that means V is equal to I into R. This is power calculation. V is equal to I into R. Current maximum 5 ampere. That means when 5 ampere current will flow, we will take 0.5 volt output from this resistor. 0.5 volt will drop across this resistor. We will design this circuit in 3 stages. Pre-amplifier, then differential amplifier, then output amplifier or unity gain for impedance matching. Here we will amplify the signal. 0.5 volt, that is at 5 ampere current. We need to amplify at a specific ratio. That voltage level will reach to differential amplifier. Here we will adjust the value, required current. Flowing current in the circuit, required current. It will determine the difference. What is required current and what is actual current. Both values will be calculated here. It will subtract the values, then it will amplify, and this final stage will drive our next circuit. We will feed this signal to operational amplifier. We will use non-inverting amplifier. We will take feedback. We will use 10K resistor as input resistor. Now we need RF. R1, R2. Our supply voltage are 12 volt. We will not consider the losses here. We will say when 0.5 volt will applied at input terminal, this operational amplifier will provide 12 volts. 0.5 volt input, that time output will 12 volt. So we need a gain V out divided by V in. 12 divided by 0.5, we need 24 gain. That means our required gain is 24. RF is equal to AV minus 1 R1. We selected R1 10K. Required gain is 24 minus 1. 23 by 10, 230 kilo ohm resistor, feedback resistor. This is our gain, 1 plus RF divided by R1. Feedback resistor is equal to gain minus 1 multiplied by R1. So our resistor value is 230K. 10K to 30K. Then we will receive this signal as an output signal of first stage. So it is pre-amplifier. So we will receive a scaled signal at the output of first stage. Then we will feed this signal to next stage, that is differential stage. Input resistor 10K and we will create differential amplifier gain. We need to adjust the gain ratio of this resistor approximately 30 times higher than this one, 20 to 30 times. If we will select 20 times, that time the current control will work slightly slower. 10K multiplied by 30, 300K, 300K, 330K, that will good. We need current adjustment here. Okay, that's good. I will connect a resistor here, 1K, 12 volt power supply. So this signal will swing from 0 volt to 12 volt. So I am using 12 volt signal as a reference signal. We will compare this signal with this one. Any signal value will be provided here that will be compared all the time with this value. This signal will try to increase, then this one, the next circuit will be activated. Now we will pass this signal through a unity gain. We will connect NPN transistor, signal transistor. This signal will connect it at this point. Now we are combining two signals here. In last session we used 330 ohm resistor, but now we will remove it. We will use 10K. When this signal will turn on, it will pull down this signal. This IC will not be loaded. Before this it was just only driving the transistor, but now we are connecting a parallel load here. Let's connect this circuit now and we will check it. Now this is output terminal. Now I will increase the heatsink size. Resistor this end will reach to preamplifier. To make it more stable, we will add 1K resistor here. So we will inject this signal to pin number 5. We injected this signal to pin number 5, and now we will connect pin number 6. Pin number 6, we will need 10k resistor connected with ground and 230k resistor between 6 and pin number 7. I don't have 230k, I connected 220k, 220k and 10k. Two resistors in series that will be connected between pin number 6 and 7, and this 10k resistor will be connected to ground. So this is pin number 6 and this is pin number 7. This resistor will be connected to ground. We have ground here and we have ground here, or we can connect ground here. The same, this ground from here to here. Pin number 7 will go to non-inverting input by 10k resistor. We will use any one, this one or this one. It is closer. Pin number 7 will go to pin number 10 with jumping 10k resistor. Pin number 10, pin number 9, pin number 8. We need 300k between pin number 8 and pin number 10. And we will connect this network. 150k, two resistors in series. It is 300k. 10k resistor at pin number 10 and pin number 7. Signal injected to this preamplifier, output of this preamplifier is injected to differential amplifier using 10k resistor. Feedback 300k. And now we need a comparable signal by potentiometer 10k. 10k, 20k, 50k. It is best option to use multi-turn potentiometer here, or we can connect same coarse and fine adjustments for current as well. You can also use multi-turn potentiometer, 10 turn, 20 turn, 30 turn, 25 turn, but this time I am not using multi-turn potentiometer. I made my own multi-turn potentiometer using a regular stereo potentiometer, stereo volume or dual potentiometer. I connected multi-turn trim pot with this potentiometer to make it some creative idea. Okay, I will connect it here. We will inject this signal to pin number 9 of this IC. We will connect to center slider of the potentiometer, wiper arm. We will bias this potentiometer with 12 volt positive and ground. This is low side signal. We will connect to potentiometer this end. Now we'll inject output of this section to next stage as a unity gain amplifier for impedance matching. It will reach to next stage, pin number 12. Pin number 14 is output. Pin number 13 here. We will connect 13 and 14 together. Now we will jumper pin number 8 to pin number 12. Jumper pin number 8 to pin number 12. You can also create a PCB using this diagram. I will jumper pin number 13 and 14 together to connect this output resistor. I will use S8050 NPN transistor, center pin base, left side emitter, base positive, emitter 685, collector 684. Collector of this transistor will reach to base of this transistor. Where this 330 ohm resistor was connected, now we will connect 10k resistor. 10k resistor will be connected at base and last 330 ohm resistor will be removed. Collector of this transistor will reach to base, emitter with emitter. Both emitters are connected to ground. Center pin base. Base will reach to this resistor. This 10k resistor which we connected at output stage. Still we need many improvements in the circuit. To run heavy loads, we need to increase the output capacitance. It is 35 volt 1000 microfarad. We need another capacitor to be connected at parallel so that the voltage will remain regulated. It is 35 volt 2200 microfarad. This one is 35 1000, 35 2200. We also need to connect capacitor at input terminal because these wires are also load. We need a large capacitor bank at input as well. If our control works nicely, then we can increase input capacitance and output capacitance. So until now our circuit is ready. We connected this A1941 transistor 28 volt to the emitter, output from collector, one resistor 10k 1 watt, emitter to base. Base is connected 470 ohm resistor that is connected to collector. Emitter is grounded D195 Darlington transistor with high gain, and we connected this using 10k resistor. In last session, while controlling voltage, we just connected 330 ohm resistor, but now we are connecting a parallel pull down. So if we will not use 10k resistor, that time this amplifier will be loaded. Its sink current may increase. To protect it, so 10k resistor is suitable. We connect 12 volt to supply two potentiometers, 50k 5k as a fine and coarse adjustment. We receive output feedback from 15k 10k resistor. We inject to pin number 2. Pin number 3 is non-inverting, pin 3 is inverting, so it will provide voltage control. Now I connected 0.1 ohm 5 watt resistor here. We will consider 5 ampere current. We will not increase than 5 ampere because our transistor is 10 ampere. For good operation, 1/3 value is suitable. Maximum half range, that means 5 ampere is top range, otherwise it will heat up and it will dissipate more heat. That time we will need some cooling arrangements. We injected this signal to preamplifier, then differential, then unity gain, and it will control the current. Let's power it up. I will use this multimeter to measure current. Always current will be measured in series. Current will flow from this multimeter. Now I will use second multimeter to measure the voltage. DC voltage. .2 volt Now I will increase the voltage. The voltage are increasing. The current is 43 milliampere. This time I am increasing the current, but the current is not increasing. Because the load maximum current is 0.48 ampere. If I will increase the voltage at 24 volts, it is drawing 58 milliampere. Now I will increase the load and we will see the behavior of the circuit. Now I will connect the second load. Voltage are 5 volts. The current is limited to 2.3 ampere. If I am controlling the current, at 5 volts, these two items are drawing 2.265 ampere current. But now if I will decrease the current is being controlled, the voltage will drop, because this time this circuit is working in constant current mode. 2 ampere current is top limit, so it will limit the current for the load for 2 ampere. Now if I will decrease the current at 1 ampere, the voltage will drop as well, because we are in constant current mode. Now our power supply is in 1 ampere constant current. If you want to increase the voltage will not increase, because the system is in constant current mode. If I want to increase the current, voltage will also obtain the setting from here. .3 volt, 2.7 ampere. If I will increase the voltage, but now voltage are not increasing than 10 volt, because the current is at 3.3 ampere. We will increase the current. Now voltage will increase again. Yes, we are controlling the voltage and current. .12 volt, 3.6 ampere is current consumption of this load. Now if we will control the current, decrease the current, the current is decreasing. We need some airflow for constant operation, or we can connect more transistors in parallel. If this video is informative, give a thumb up. If you have any question, please write in the comments. Thanks for watching. Assalamu alaikum wa rahmatullahi wa barakatuh.